Okay, good afternoon, everybody. So let's today finally I am going to finish this session which cover linear basis function models and Bayesian linear regression. So it is a bit more mathematical, but if you try to understand it, I will cover each and aspect of the equations covered in this slide. So please do focus on these things. Okay, great. If you remember, I in lecture 4, Introduction to Linear Regression, I covered some part of what is linear regression and what it is. So this first slide is introducing the same. The simplest linear model for regression is one that involves a linear combination of input variables. So now I don't want to introduce everything you know. For an example, what is x and what is w. So here we assume that this is x1 t1 x2 t2. So this kind of data is given, and there are, let's say, n instances are there up to tn. So this is the whole data set that we are having. We want to fit this data set with some polynomial using linear regression. What we generally do, we assume that there are some weights w0, w1, wd. If my x, if this x could be a vector, right? So this x we can say this is x1, x2 up to xd. So there could be d dimension. So this x vector could be of d dimension. So when you do linear regression, so this w is again, this w is also vector of d dimension. So if you write w into vector form, it is like w1, w1, w2 up to wd. So this is also d dimension vector. When you do dot product of it, w dot x, it means w transpose x. You get this form. So you get w1 x1 plus w2 x2. This is how you do in up to wd xd, right? So this is a linear regression of and we represent it like this. In short note form, we can write it like this: from j equals 0 to d, where this wg and w0, if x is if x is having d dimension, so we assume that x0 equals to 1 always in this case, to write into this notation form, right? So for the short representation, what we do, we always assume that x is 0 equals to 1, and for this makes us to represent directly into the vector form. What we can do, wt w transpose x. So w is w1 and w is also vector, x is also vector, but now whatever x is having from x1 to xd, it is already there. And now now we have introduced one more component, that is x0 equals to 1. So this is x0. So you know all these things, right? We have covered in much detail in lecture 4. Now this is the error function. We had a discussion over that, if we want to fit a linear regression model, how we do that. We generally, if this is a line I want to fit to these points, so I take any line. That is of form w0 plus w1x. This is, let's say, x-axis, and this is, let's say, y-axis. So I want, what I do, this is my line. I take this error, this error, this error, and I add these errors. I square this error, I square this error, I square this error, and I add it. This is my error function, right? So whatever I am doing, this is nothing but the value of a line corresponding to x. For an example, this is a line. So if this is my xn, so the value of yxn will be this. So I am doing what I am doing. I am subtracting this value from of a line by my given value in the data set. So let's say this is my T to Tn. So this value is given in my data set. I'm subtracting it. So in general, you know this what I am doing. I'm just adding all the errors that is of every individual point. I'm squaring it. Why I'm squaring it? So that for an example, it may be possible that this error is positive and this error is negative. So they can they can cancel each other to avoid that situation, or to optimize for optimization perspective. Also, we are doing the square. So this is the error function. This is I think I have covered it more than for 5 6 times so far in the lecture series. So this error function more elaborately, if you will see this, what is this error function is, this is my target variable that is in the data set. This is my value given by my hypothesis. What is my hypothesis? That is nothing but W0 x0 plus W1 x1, whatever it is given. So this is my this thing. In short form, I can write this thing into this thing in a vector form, wt transpose x. Everything is all things are remaining same. So now the important step, which I think you have not seen so far, is this step. I can write this equation. For an example, this is equation 1. I can write equation 1 in this form also. What is this form? This is a matrix form. Let's try to understand why I can write it like this. So if I see this thing, this x is a matrix. So this x is a matrix, and it is having my first vector x1. Let's say this is my first vector. So I told you that in my data set there are n samples: x1, x1 t1, x2 t2, x2 t2, likewise xn, xn tn. So there are n samples in my data set, right? So and now this is my first x1 first input, and first corresponding to first input, this is my output value. This is my second input x, and this is corresponding to second input value. This is my output. So I can write all these x1 x2 up to xn into a matrix form. So this is my x1, this is my x2. Likewise, I wrote all these x in my matrix. Why this is matrix? Because this is matrix of size of dimension n into d. So each row corresponding to each input. This is first, this is second, this is nth input. So each row corresponding to the each input x, and the width of this is, because this is a vector. So how can I can write, this is my first component, this is my second component, this is my third component, and up to this is my dth component, right? So this matrix is of size n into d. Now when I multiply this thing with w, so this is let's say this is my weight vector w, and I write this w as w0, w1 up to wd, up to wd. So this is my weight vector. Now if I do, yes, so if I multiply this matrix, what I will get, my first row will multiply this whole column. So what I will get, x, for example, I am writing, this my superscript is telling which sample it is, and this subscript is telling which component it is. So x1 1 into w0 plus x1 1 2 into w1, sorry if it is x0, right? So this is x1 w1 up to x1 dimension d into w d. This is what I got when I multiply this row with this column. Again, I multiply this row with this column. What I will get? x0 to w0 plus x1 to w1, likewise xt to wd. So this is what I got in my second row. If you see this carefully, this is what it is. This is the value of y. This is the value of yx. So this is nothing but a hypothesis. This is y x1 w. What the second row will get? What the second thing will get? Second I will get. This is y x2 w. So this is x is a matrix of size n into d, and this vector w is of size d into 1. So the resultant of this both product of x into w will be n into 1, right? What this n into 1 will be having? This will be having y x1 x1 w y x2 w. Likewise, I am having all these things up to y x and w. So this vector will be having, so the resultant of these x into w, the resultant of x into w will be a vector that is having the value of y x1 w y x2 w up to y x and w, right? So this is simple. What it is, what actually it is what my hypothesis is giving the value, what my line is giving the value. For example, if this hypothesis is a line, so what is the value that my line equation is giving when when I am feeding the value my x1? What is the value that I am getting from the line when I am getting x2? For example, if this is a line, so what if this is a line, so what value I am getting if I am feeding the value of x1? So this is the value of what I am getting w1, right? What is the value that I am getting from the line when I am feeding the value x2? So let's say this is the value. So this is what my hypothesis is giving. Now I am subtracting this hypothesis value in a vector form from t. So t, what t is? T is again the vector that is this t1, t2 up to tn. So this is these values what I am having in my data set, right? So these are the values what I am having in my data set. So when I am subtracting t from my just a minute. So this expression, what this expression is saying? This expression is saying I am subtracting this value. I am taking this value first, and I am subtracting y x1 w. Similarly, I am subtracting t from t2. I am subtracting s2 w. Sorry, this I just wrote differently. Why I am doing this? Sorry for notations, but this is t1, this is t2, this is tn. So what I am subtracting my hypothesis value from first hypothesis value from t1, second hypothesis value from t2, and likewise I am subtracting from tn my nth hypothesis value. So this is nothing but the differences, right? I get all the differences in a vector form. So when now if these are the differences in a vector form, I am transposing it. What do you mean by transposing it? For example, this is x1, x2, x3. If I transpose it, what I will get x1, x2, x3, right? So this is a transpose. And if I multiply this transpose with actual vector x1, x2, x3 again, so just for first focus on this. I will address all these questions later. If you miss this point, you will lose all the lecture. So for an example, if this is my vector x1, x2, x3, the transpose of this vector will I can write like this, right? This is the transpose of this vector, and this is actual vector again. When I multiply it, what I will get? I will get x1 square plus x2 square plus x3 square, right? So this is nothing but is the sum of the squares of each component. So what this vector is? This vector is having first value this one, second value this one, and nth value this one. So when I multiply the transpose with the actual vector, what I will get? I will get the sum of the square of each component. So what I will get from this? I will get t. What I will get from this? For an example, the first value will be t1 minus y x1 w whole square plus t2 minus y x2 w whole square. So likewise, I will get up to tn minus y xn w whole square, right? So this is nothing but the other way to represent the same thing. So sorry for this messy presentation, but to just to highlight, here it is. So this is this thing, and this is this thing. This is something different. So and this is just to. So these are the so what from this explanation, what I'm saying that if you have some error function and you're writing that error function in this form, similarly if you want to write into a vector form, the equivalent representation of the same expression will be this. So don't get confused if you see all these things. Now very simple, and so as I have done this thing several times. Now if what I do, I take the gradient of it because I have to maximize this function. What we generally do in maximum likelihood function, we had an error function that correspond that is changing with the value of w, right? Now if I have an error function, that value may change when I change the w. So I want to find out that value of w where the error function is minimized. So what I will do, I take the differentiation of this equation with respect of w. So what I will do, this is my error function EW. I differentiate it. With the w and put that value equals to 0. When I solve that value for w, I will get this expression. So this result of for w is in closed form. If somebody asks you to derive the value for w in a closed form, you can follow these steps. So for this step, when you have to differentiate it with respect to W, you need to see little matrix calculus. Matrix calculus. It is not very different, but you need to see few steps how you do differentiation using vectors. So I am here differentiating this EW expression with respect of W vector. When I differentiate, I get this expression. I put this expression equals to 0 just to find out the value. Now when I do it, I will get, just to simplify it, I get W equals to X transpose X the whole inverse into X transpose T. Okay, let's take some questions. So first question is, yeah, so sorry for that. Somebody is asking, sir, you have written W which maximize the function, which need to minimize it, right? This error. Fine. Right. You are right, sir. So this is the error function. We need to minimize it. I believe W is a slope with what, but what is T? So W is not a slope. W is not a slope. W is a vector. W is a parameter. And T is a vector again. T is a vector again. If you look carefully, this is T, sir. This is T. It is a T is a vector of your input value, that is T1. What is this? This is T1, T2 up to Tn. So T is a vector. Here missing will be half between both. So that half is a constant here. So somebody is asking where that half is gone. So half was there actually, but if you, because you finally you need to maximize the function or minimize the function. So if there is some constant, you can ignore that while finding out the minimum and the maximum. So this is just a half is a constant. You can ignore them. So if you find some type of inconsistency that I have written half and the next step I missed it, so it means that I am just ignoring it. So that's not a problem. You can write half as well there also, but while you take the differentiation and you put it equals to 0, that half will go away. So that half is there, but we can ignore them. While how do we differentiation? So differentiation, I told you, this is a matrix calculus. And you need to see the step. So these steps are very similar. How do you differentiation in that univariate calculus? Can you open the question to all the attendees? It will help to us to follow. If T is an input vector, then what is X? So if you see carefully, Amey, that your input vector, input data, that input data is in which form, sir? If you look carefully, this is your input data, right? This is X1. This is X1. Corresponding to the input X1, there is a value T1, right? This is X1. There is a corresponding value T1. Second value of that there is X2 and the corresponding value is T2. Likewise, the nth X is Xn and the corresponding value is Tn. So likewise, you have X as a vector and T is a real number. So when you put all these T's into a vector form, what do you mean by corresponding with value T? So please, if you ask these kind of questions, it is very hard for me to go through these steps. You are asking what is T? This is a function, right? I already told you in previous so many lectures that for every input there is a X and Y type of pair that you get in data set. For example, you assume that if you feed X value to some function, that you will get some value Y. So if I am writing X comma T, it means that you are feeding some value to X and you are getting value T. So in learning, what do you mean by learning? You need to identify what kind of function is this. So for every given value, you need to find for unseen values of x, you need to find out the new values of new values. So for an example, when you feed this x1 to function, you will get t1. When you feed x2 to the function, you will get t2. When you feed xn, you will get tn, right? So this is what is this is function. So don't ask these questions because this is too late for you. You should work hard in previous lectures. So I hope that this t is input vector. So the one question is, if t is input vector, then what is x? So I told you that t x is like because the input is input is in form of x comma t. So when you write separately x in a matrix notation, then you will get a bigger matrix x. So when you write, I already told you this is x, right? X could be a vector here. It may have a d component, and t is a real number. So x belongs to a d dimension vector, and where t belongs to only a real number. So this is all the things are covered. I don't know why. Okay. So what are basis functions? So one question is, can you enable options all participants so that we can see questions as well? I will ask that guy, but right now I don't know. In the later after a break, I will do that. Okay, so basis function of a motivation, basis. So basis function of a motivation is, for an example, you need to, for an example, this is what we need to do. Somebody is asking you to uh, classify this. For an example, this is a data set. Somebody is asking you to, if this data set is linearly separable, you can draw a line, right? All the points that belongs to one side, you can classify them into class, let's say C0, and the points belong fall to the other side of a decision boundary, you classify them into another class, right? So this is a binary classification problem. And in linear regression, because we have a linear boundary, we can, because this data is linearly separable, we can draw a line that can separate these things very accurately. Now every time if somebody gives me a new x, and let's say this new x is here, this falls here. Let's say this is a new x and it falls here. So somebody asks me, well, please classify it whether it belongs to C0 or Cx. So because this point falls to this side of a linear decision boundary, I will classify this new point to as a C0 class. So this is what we generally do in linear classification. But sometimes what happens when we don't have, when the data is not linearly separable, then can we still do a linear regression? Is there anything that what we can do? So what this figure is showing, that yes, this is not a hopeless case if the data is not linearly separable. If the data is not linearly separable, still what you can do, you can project them into a higher dimension space. For an example, this is a two-dimensional space. This is a two-dimensional space. You project them into a higher dimensional space, let's say into R3, and let's say they come into this space like this. Now you can, here in this figure, you can see that you can draw a hyperplane, which hyperplane is similar in analogy. What you can understand, hyperplane is similar what you have if in 2 dimension you have a line, in 3 dimension you have a plane. And in n dimension you have a n-1 hyperplane. So in this 3 dimension plane, in 3 dimensional space, you can see that you can draw a plane which can actually comes in between of these two classes that are red and blue. So here we can see that with this data in this space is linearly separable. So the motivation behind it, if you have a data in a small dimension space, you project that data into a higher dimensional space. From that higher dimensional space, what you can do now, if the data comes into a linear separable, if data comes into a linearly separable form, you can draw a hyperplane between that, and then you can classify it. Once you will get a equation of this hyperplane, when you go back to your actual plane, you actually see this non-linear line here, non-linear curve corresponding to this hyperplane. For an example, let's say, just this is not a very great example, but you can see the intuition behind it. For an example, there are some points here, and there are some points here. What you need to do, you need to classify, you need to find out whether they are linearly separable in a bigger space or not. So what I can do, rather than projecting into bigger space, let's say this is my x1 and this is my x2, what I do, I make the new axis, and that is x1 square, and this is x2 square. I'm squaring every number because they are very near to the origin. And if, let's say, they are all between 0 and 1, this is my origin 0 and this is 1, this is -1 and this is 1, so they just come close to here. They just come close to here. These all points come to this space, and all these points which are farther, they becomes more away from the space. So they become more away from the space. You can use this example with the numbers, and you will see that, yeah, actually the numbers which are very near to the origin, they comes more closer to the origin, and which are very far away from the origin, they comes into this quadrant, and they go away far from the origin. Now you can draw the linear separable line here, where you see here that you can not draw a linear line here. So this is a basis function motivation. What you can do, you can project your x into higher dimensional space. So we specify the set of functions phi1, phi2, phi-m. So phi-m from x to r. So what it is doing, we will see example. It is nothing but we are giving, these are my different functions, that is phi1 to phi-m, and every time I am giving my input vector x to it, and it is giving me some real number. Again, I am giving some vector to it, this phi-m function, it is giving me some real number. So these phi are different functions which, when I am giving my input vector x, so this give me a real number back. Now I can have multiple basis function. Just to before reading this slide, I want to give you a simple example. Let's say, for an example, a very simple linear basis function could be this phi0 x equals to 1, and this phi1 x equals to x only. Now when I do phi0 x equals to 1, I know that, and this phi1 x is x. This is univariate case. Let's say my x is not a vector in this case, and x is a univariate case. So univariate case means this is just a mirror function where every time I give my value x, let's say x equals to 2, so it will give me back 2 only. So this is a univariate case. Here x is not a vector. So this phi1 x is x and phi0 x is 1. Now I can find W0 and W1 with corresponding to it. I multiply these things and add these things. So this is like this, because my phi0 x was 1, so this 1 will go away and this W0 will remain same, and W1 x will get here. So I can represent in a very simpler form my basis function like this. But as you can see, there is no use of this basis function, because we cannot do already these things without basis function. But from this example we can understand what actually is basis function, and it is nothing but we are replacing we are converting x into higher dimensions. If x is a multivariate case, so this is a univariate case. If x is a multivariate case, what I can do, my phi 0 x equals to 1 only, and I give my this vector, this is vector, right? It is having d dimension. I am giving all the vector, and it will return me my first component only. So this x is a vector x1 up to xd, right? So my first basis function returned me the first component, my second basis function returned me the second component, and my dth basis function will return me the dth component only. So what I am doing here, that I am multiplying my first component with some weight, second component by second weight, and dth component with dth weight, and this phi 0 x equals to 1, so this w0 multiply by 1 equals to w0. So I can represent this as my in a multivariate case, in a multi-dimension case. So again, this is just an example to see and understand. If you see this kind of notation, you shouldn't get scared or what like how can I understand it. So this is a very simple case and example. Sir, how do we get this phi 1 and phi 2 etc.? So there is a question, so how do we get phi 1 and phi 2 etc.? So this is a design problem. You need to design a matrix. We will see it, right? So this is a design problem. You need to be very creative while designing or coming up with these basis functions. Creative means that there are a lot of standard ways you need to follow them. We will see. So more typical case, if x polynomial regression, right? So that was the polynomial regression. So if you have only a x is a one dimension case, so x is a vector that is having only one component in it. So it is having only one component in it. So this is this case. Now, so there is a question from some student. X0 to XD are attributes of sample. Not samples. It is a sample. So I could have like multiple samples x1 t1. This is my first sample. x2 t2. This is my second sample. Up to xn tn. This is my nth sample. In this sample I have input, and corresponding to this input I have output. So this is in this form, fx equals to t, right? So for when you say I am saying x0 to x2, it means this x is a vector here. So you can represent this x as x1 up to xd. These are the d dimension vectors. When I'm saying x is univariate or univariate, it means this x is only having a one component, only one component in it, right? So this is my this x is my univariate case. Now what I am saying, that for every x you take the basis function such that the ith basis function will be having the that I power 2x. So for an example, I try to find a polynomial of m order. What I can do, I can take m basis functions, and for I can take m basis function, and first basis function this phi 0 x will be 1, phi 1 x will be x, phi 2 x will be x square, and likewise phi m x will be x to the power m, right? So this is my m, this phi. Now if I want to design a polynomial of order m, I can take m basis functions, and what it can do in a univariate case, it just make the power I to that x. So here I am having m basis function. I am multiplying these each basis function with some vector. So here this is w0, w1 x1, w2 x2 up to wm x1. So likewise Here in this case, what I am doing, I am creating my m order polynomial in a univariate case, right? So there is a question again, sir, how this choice of basis function is decided? That's what I am discussing. So if you want to say, find out this, so this is a question of a model selection, right? So please don't go think too much about it right now. Try to understand what exactly on the PPT. Don't go. So for an example, just to be very simple, if you want to fit some, this is a data set. So this is a data set given, and you need to fit this data. You know that this is, if this data set is not linearly separable, you need to fit it with some order function. So if you come up with, let's say, I want to fit it with three-dimension function or cubic function or nth order function, nth order polynomial, you need to take nth different basis, and you need to do make accordingly. That's simple. So now this was a case when you have a univariate. If you have x, if you have a x as a vector which having d dimension. So without going in general, I am just writing a specific example. So here x is x1, x2, x3, and I want to find out the polynomial of order 2. So of order 2 means ax plus bx square. So this is a second order polynomial, right? Where the maximum degree can be 2. So I want to design this polynomial. What could be my basis function? So my basis function, because I decided that my degree polynomial should not be greater than or equal to 2, it means this is what is actually I need to follow. So when I take my first basis function, this is my first basis function is f phi 1 x. I just take directly my x1 first component. Likewise phi 2x my second component. Phi 3x my third component, right? So because the sum could not be greater than 2, so what I am doing, I am taking this equation x1 plus x2 plus x3 such that all the combinations of x1, x2, x3 that must have value less than or equal to 2, less than or equal to 2. So first I take all these values of x, all the sum which are equal to 1. When I am having sum equal to 1, it is nothing but I am having the power, these component x1, x2, x3, right? When the sum is 2, now I'm having a degree 2. So it means that phi of, let's say, 4, phi 4 of x, phi 4 of x equals to x1, x2. So this is x1, x2. So I need to find out all the combination which can give the degree 2. This is x2, x3, and phi 6 of x equals to what is left now? X1, x2, x2, x3, and likewise x3, x1, x3, similarly x2, x2, and these all cases are written here, right? Finally, when all these these cases are over, what you left with? Square terms. So this is x1 square, x2 square, x3 square. So likewise, you can have a basis function in d-dimensional form. So this is just to explain you what is a basis function. Don't so once you decided that I want to put my input vector x into higher dimension space. Let's say 2 dimension. This is my 1-dimensional space vector, and I want to find I want to map into 2-dimensional space. So what I can do, I can come up with a basis function that is that is having the maximum degree 2. But if I want to map my polynomial into n-dimensional space or 3-dimensional space, then I can come up with a basis function that is having the nth order or third order function. So somebody is asking, sir, I don't understand why x1 plus x2 plus x3 is less than 2. I don't know. This question is quite trivial because the degree cannot be maximum more than 2. Okay. So the next so these are some other kind of basis function. For an example, this is the Gaussian basis function, sigmoid basis function, and logistics basis function. So in polynomial, other than polynomial, you can have these other basis functions also. So right now I don't want to go into the detail because my motive is not to discuss the basis functions here, but how to use the basis function in linear regression. So this is error function again. Now rather than writing my first, if you remember, I was writing wi into xi, right? And I was wi into xi, and that was a summation here. Now I just replaced my x with the phi function. So this wi got converted into phi ix, right? So this is wi into phi ix. Everything remains same. Everything remains same. In a vector notation form, this is phi x. So what is this phi x is? This phi x is, so this is a vector. So this phi x, how can you write it? This is a vector, right? So this is phi 0 x, phi 1, phi 1 x up to phi m x. So this is a vector. So this phi x is a vector, right? This phi is a vector here, and I'm transposing it with w. So because it's m dimension, so my vector, the weight vector should be m dimension. When I multiply my w0 up to wm dimension vector with this is a transpose. When I multiply it, I will get, if I multiply this with this, so what I will get, w0 into phi 0x. Likewise, wm into phi mx. So this is same, right? So this is same. You don't get, you shouldn't, you should understand it quite easily. When I write this same thing into a matrix form, this is what I get. I don't need to explain it again because I have already explained it into the previous slide. So there is one question. Can you please simultaneously discuss the practical application of these mathematical expressions that we do need to use these, as this will help us to visualize and can make the topics more applicable. So for an for right now, you should what I am telling you, how to fit the linear regression. So the practical applications is similarly the same. How to find out the function. I need to discover the function, which function is generating what. So if I have some data set, I need to find out, to find out the true function which generated that. So this is, I don't know, true applications could be vary from one place to another place, right? For example, there is a customer in a bank, they are coming, and how much that bank customer will spend. So I need to find out, so I can make a data set with that customer have different attribute, age, name, sex, and all these things. And if, for example, I have a data set with all these attributes, you spend 5,000. With other attributes, you spend 6,000. Now I am having a data set. I can come up with a function to predict if a new customer come into the mall or a hotel, how much how can he much spend. Accordingly, I can put a menu in front of him so that that menu come into his range. So there you should creatively think yourself what could be the function. Read be after this classes too, so you will get a more clear idea. So in machine learning, we are trying to fit come up with a true function, and that true function could be vary from one field to another. So this is a vector form, and now again this error function. So this q, if you see carefully, what this q is, this matrix. This q is this matrix, when I am multiplying it with W. So this I told you that I have M basis functions, and therefore I must have M M weight components also, or I should say more specifically that the dimension of a weight vector is M. When I multiply this matrix that is of dimension n into M with with this matrix M into 1, I will get n into 1, right? So this is nothing but phi sigma sigma 1 to M Wi phi I. Likewise, this belongs to this row, and similarly, I equals to 1 to M Wi phi I x n, right? So this belongs to this belongs to the product of this row with this column, and I get this. So this is nothing, and when I got this is the value that my hypothesis is giving. I need to subtract to find out the value of how much my hypothesis is differing from my input, my data output. I told you that this is how I get x1 t1 x2 t2. So this value when I feed into my hypothesis, I get some value, and this is the actual value. How much it is differentiate, how much it is differ from the hypothesis. I'm just taking it and squaring it. So this is nothing but the square, sum of square. So when I write it, it will come into this form. I need to differentiate it to find out the minimum of it, right? I need to differentiate it to find out the minimum. So this is when I differentiate it. So this is the same function. This is same function. I just multiply it. So I can write this notation as T transpose minus Q W transpose. And this transpose you can write W transpose Q transpose. So this is finally T transpose minus W transpose. You need to see all these things. So when you multiply this thing with T minus QW, you get this thing. So this T transpose, TWQ transpose, and all this, you finally get these notations, right? And because I am differentiating with respect to W, this is a constant term here. I can ignore it. I can ignore it means to say it will get 0. So finally I will get this term. So I am differentiating with respect to W, it will go away. It will go away and this transpose get converted. So to Q transpose T will get away. And here this is a constant, it will come out Q transpose Q. And I left with W transpose W. So W transpose W is nothing but, for an example, this is nothing. I can represent it like W square in its simple form. So it is 2W, right? So 2W means this 2 will come here and this W will get here. So W transpose the W, when I differentiate it with respect to W, I get this expression. Putting it to 0, I get this. And finally, I get the value W equals to this. So if you remember at first, when I was not using my basis function, the value of W was, it is with basis function, right? It is with basis function. When I was not using basis function, it was like X transpose X inverse X transpose T. So it was like this when I was not using basis functions. So it is with basis functions, and it is without in a simple case when I am not using. So the only difference between these things is the matrix. Every time I change my basis functions, this matrix will get changed, and it will this matrix will change, and this matrix is known as a design matrix, right? Conveniently, you can put any linear, non-linearity, whatever you want. For an example, if you want to put into n-dimensional space or t-dimensional space, so you can choose accordingly what is that basis function you want. So this is the only difference. So you need to see, somebody is asking why this transpose get converted also. You need to see this matrix calculus. It is easy, but you need to look at it. Now finally, if you recall from the fourth chapter, we had used regular expression. Oh, sorry, not regular expression, regularization. So regularization, whatever I was saying, that whenever if you want to, if you have an error function, so if you do least square error, if you do least square error, what happens? It will fit the data. If you, for an example, these are the 3 points, and if you are using constant line, horizontal line, this is the line that maximum you get this. For example, this is the best fit line you can get. As you increase the order and you want to minimize the error, the, it will get into overfitting. This is all we have discussed very elaborately. So it can lead to this sum of square error minimization can lead to overfitting. To avoid that overfitting, we are adding some terms, some regularization term, that is half W transpose W. What it will do, it will help you help you to have a constant over the value of with these weight vectors, so that they will not grow largely. Every time this weight vector grow, the value of W grow, it will add to this error function, because the motive is to minimize the error function. Somewhere it will again drop these larger values to the small values, because you are adding it. It is already discussed, so I'm not going to discuss it again and again. So the important point is, this is the error function that you have, this is the regularization term you are having, and how much weight you are giving to this regularization, it depends upon the lambda. So now my new error function will be this plus this regularization term with this factor. So half again is used because lambda is a constant, right? So I can normalize it with lambda by 2 also. But you can see this 2 will get will be good when we used analytics and we try to simplify the expression, that this 2 will help us. So now this is a regular expression. When I'm doing some calculus on it, linear calculus on, so when I'm doing matrix calculus on it, again I'm multiplying it. So I get this expression T transpose this and plus this. When we are differentiating it with respect to W, this goes away. This is a constant, right? And this is again this T transpose Q get converted into Q transpose T. This two goes outside. So these are the constant terms here. So this again W get converted into 2W, right? So 2W will get converted here. So here there is a hidden 2 here, there is a 2 hidden here. And when you converted this W transpose T, it will get again 2W here. So this will be get again 2W. So there are 2W. When you take all these three in common, the three two three twos in common, and you get into other side, because here is a 0, they all get into 0. So finally you will get this W. You will get this W. So this is what you get when this W weight vectors are those weight vectors when you do regularization. When you don't do regularization, what you will get? Q transpose Q inverse Q transpose T. And when this is with basis functions. This is with basis functions. And when you don't have basis function, this is, oh my god, what I did. Q transpose Q, okay, this is this. So when you don't use basis function, this is X transpose X inverse X transpose T. So these are the three different forms which we have discussed so far. and this lambda 2 becomes lambda, right? Lambda 2 becomes lambda because this w will get 2w, right? And this is lambda by 2, so t2 get cancelled. This is a algebra. You need to see it. So this is algebra. No, no, this is not this 2. So you will see that, it will get simplified. Uh, Let me see. Minus 2 t transpose, so that is 2 to q t transpose 2, and this is w transpose t w. Okay, and this is. Mhm. So I will get clarified this to this if it is there is a calculus. So this is what we have discussed so far. I will take this question one after the break if there are so, and let's stop here now. So there is a question again.